So, in this section we will discuss electromagnetic wave propagation in absorbing medium. We have seen the propagation characteristics of electromagnetic waves in dielectric medium, isotropic dielectric, and now in an absorbing medium. Mostly absorbing medium, primarily they are conductors, conducting medium. So, today in this discussion the following topics will be discussed, that the transient decay of free charge in a conducting medium. Then we will address the wave equations for the conducting medium and the resulting plane waves. Phase, we will look at the phase and amplitude of the electric field and the magnetic field of the plane waves. Then we will categorize the good conductors and poor conductors. We will see that the electromagnetic waves cannot propagate in conducting medium. As a result, there will be only a small skin depth penetration of the electromagnetic waves. We will characterize that and look at the quantity expression, how it depends on the propagation and the frequency of the electromagnetic waves. Then we will see the average power dissipation, Joule's loss in conductor. So, a conducting medium, we will look at the Maxwell's equation. For example, conducting medium, salt water, metals. In such a medium, the charge flow cannot be controlled and the current density due to free charge carriers is not 0. Free current density J f is given by the Ohm's law sigma into E. There should be a vector here. So, now we look at the Maxwell's equation. In this case, del dot E equal to free charge rho f by epsilon, and the curl equation for the electric field del cross E equal to minus del B del T, then del dot B equal to 0 and del cross B equal to J f, the current density due to free charges, and mu into epsilon del E del T. So, this J f is equal to sigma into epsilon, which will substitute in place of J f and will reorganize this Maxwell's equation to form the wave equation. Also, we have this equation of continuity, that del dot J equal to del rho f del T is the free charge, rate of change of the free charge. Oh, there should be a minus sign, and then this J f is the charge density, current density due to the free charges. Now, Ohm's law states that J f equal to sigma into E. Gauss's law gives you that del dot E equal to sigma rho f by epsilon. Now, if I combine these two equations, then we can write that del dot J is equal to del dot J is equal to sigma del dot E, using this equation in this, and then if I use del dot E equal to sigma rho f by epsilon, then I can write del dot J is equal to sigma rho f by epsilon. So, I have been able to write an expression which relates this J f and rho f through sigma and epsilon. Now, because the left hand side of this del dot J is equal to del rho f del T, and the right hand side, this left hand side is equal to this, which is equal to this. So, I can write del rho f del T is equal to sigma rho f by epsilon naught. So, equating this to this, we can write this, the equation of continuity, in this form, that del rho f del t is equal to sigma rho f by epsilon. And if you solve this equation, this gives you the solution rho f equal to rho f 0, that is at time t equal to 0, the free charge, times e to the power of minus sigma by epsilon times t. So, it shows that the free charge decays exponentially, and the decaying depends on this factor sigma by epsilon naught, that is the conductivity and this sigma. So, free charge density dissipates in the characteristic time tau sigma by epsilon by sigma, that is the time over which the charge decays to 1 upon e times of the original. So, looking at this consequence, we can classify the conductors if sigma tends to infinity and tau, this characteristic time, the dissipation time, is equal to 0, that is instantaneous, then it is a perfect conductor. And if sigma is large, reasonably large, and tau is small, then this conductor is a good conductor. But the reverse will happen if sigma equal to small and tau is very large, that is the characteristic time for charge dissipation is quite large. In that case, the conductor will be classified as a poor conductor. So, this equation that rho f equal to rho f 0 e to the power of minus sigma by t into t, sigma by epsilon into t, it reveals that if some free charge is placed inside the conductor, the charge flows out immediately to the edges, that is in no time the charge dissipates. So, we will not consider such transient behavior while looking at the electromagnetic wave propagation in a conductor. Therefore, we will put this free charge rho f is equal to 0 in the equation arising out of the Maxwell's equation. So, del dot E equal to 0, del dot B equal to 0, and del cross E equal to as it is, and del cross B will now be represented as mu sigma E, which is for j, that is j equal to sigma into A and mu epsilon del E del t. So, this is the new form of the Maxwell's equation when we have used this rho f equal to 0. Now, if we take the curl of the equation del cross E equal to minus del p del t, that is the third Maxwell's equation, taking the curl on either side. So, the left hand side gives you del cross E, which is equal to del of del dot E and E of del dot del, which is a very well known identity, and this identity in this case will result in only minus del square E, because del dot E is equal to 0, which has come from the consequence of this equation. So, as a result, we can write this left hand side del cross E is equal to minus del square E, and the right hand side, that is minus del B del t. If you take the curl of this, so you have to write minus del t of del cross B, which is equal to minus mu epsilon del square E del t square minus mu epsilon del E del t. This has come from this equation. I take curl of del B del t, which will be equal to mu epsilon del E del t plus mu epsilon del 2 E del t square. Exactly that is what is written here. So, I have been able to calculate the del cross E and del cross del B del T. So, equating these two, we can write this equation del square E equal to mu epsilon del square E del T square plus mu epsilon mu sigma del E del T. This is for the electric field, and if we proceed by taking the curl of the fourth equation, that is del cross B del cross B, then for del cross E, if I write this, and also for del cross E, if I write this, then we can arrive at this equation del square B equal to mu epsilon, which is a similar equation, except that E is now replaced by the B vector. These equations, if you look at these two equations, these equations admit plane wave solution. So, we will look for the plane wave solution, and we will try and look at, and on substitution of this plane wave solution into this equation, we will see what is the nature of the propagation constant, what is the amplitude of the electric field and the magnetic field, and is there any phase relation between the electric field and the magnetic field. So, accordingly, we assume a plane wave solution, consider an x propagating electromagnetic wave. So, in that case, we can write this electric field, it is propagating along x as a function of x, but it is polarized in the y direction. So, we can write this equation y cap E naught e to the power of I k x minus omega t. Substituting this equation into the wave equation, that is del square E equal to mu epsilon del square E del t square plus mu epsilon del E del t, we get that for an operator del square E operating on this equation, plane wave equation, we get I k and I k twice. So, that gives you minus k square, and operating twice, that is taking the time derivative twice, we will take out I minus I omega twice. So, that gives you minus omega square multiplied by mu epsilon, and del E del t will give you I into omega times mu into omega. So, this equation when substituted with this solution, then we get that minus k square equal to minus mu epsilon omega square minus I mu sigma omega. All of them are having a minus sign. Now, it tells you that the square of the propagation constant is also imaginary. That means, the complex k of the form we can consider that k is k plus I k minus, and if you take the mod of this k square, k square will be equal to k plus square plus k minus square minus twice I k plus k minus. So, you have been able to write the imaginary part and the real part for k square, and now we can compare these two equations, k square equal to this, also k square equal to this, and on comparing we get that k square plus k minus square is equal to mu sigma omega square, whereas k plus k minus, the product of these two quantities, the real and imaginary part of the propagation constant, will give you mu sigma omega by 2. So, we have been able to see the complex propagation constant whose real part is mu epsilon omega square and the real and the imaginary part is this. Of course, this is the real and imaginary part of the k square quantity. So, k square equal to, we can write that mu epsilon omega square plus I mu sigma omega. So, this on solving, because I have these equations k square plus k square minus, then k plus k minus. So, I can use this with a 2 and then you minus 2 into this, then we can add, you can frame k plus minus k minus square, which will yield the solution of this k plus minus. The k plus and k minus put together will give you the solution of this equation, is a quadratic equation whose solution will be this. So, once it is plus 1, next for the plus value of k and minus 1 for the minus value of k. So, the plane wave solution, having known that the k, the propagation constant, has two values k plus and k minus and can be written as k equal to k plus I k minus, we can write the plane wave solution. We can rewrite in fact the plane wave solution as E0 e to the power of minus k minus x into e to the power of I k plus x minus omega t. In fact, you can see that this part accounts for the phase, k plus is the real part of the propagation constant, k minus is the imaginary part, and this imaginary part has given you the attenuation of the amplitude E 0 e to the power of minus k minus x. So, it tells you that the amplitude of the electromagnetic wave which is travelling along the x direction in a conductor decays as e to the power of minus k minus x. So, this k plus and k minus, these two quantities are given by this, which are the functions of omega, epsilon, mu and sigma. So, all these four quantities are going to decide the k plus value and the k minus value, that is how, what will be the phase, instantaneous phase, and what will be the loss in the amplitude of the electromagnetic wave in the conducting medium. For the magnetic field, we know that B equal to this can be connected to the electric field through this equation. Now, since k is complex, B and E, they are connected by a complex quantity. That means, the phase related with this k will also be attached to the phase of this electric field, and in general electric and magnetic field will have a phase difference. And writing this B field in term using this electric field value known, we can write in this equation. So, k by omega, which is a consequence of this equation. So, I am trying to write this the magnetic field in terms of the amplitude of the electric field, the attenuation factor of the electric field and the phase of the electric field, but this is a complex amplitude. So, let us look at this. So, we could write the electric field as this and the magnetic field in the same way, k by omega and the electric field quantity, but you can see that they are oriented in a mutually orthogonal direction. This is along the y direction, this is this electric field direction is y, that is an y polarized electromagnetic wave, and the magnetic field is along the z direction. Now, this k plus and k minus, these two quantities which constitute the complex propagation constant can be written as k mod into e to the power of I phi, where phi is the phase of the phase factor associated with this propagation constant, and this phi, the value of the phi will be equal to tan inverse k minus by k plus. So, this is the phase that is associated with the propagation constant, and we will see how this phase is going to be related to the phase of the electric field and the magnetic field. Now, we could write k equal to k e to the k mod e to the power of I phi, with phi equal to this, and this is the relation which connects electric field and the magnetic field. K, therefore, k decides the phase of B with respect to E. So, let us see that we can write this B and E in this form, as we have seen B and E, they are no more in phase. So, we attach different phases delta E for the electric field and delta B for the magnetic field. This, and we also recall that k has a phase of e to the power of phi. So, we have three quantities: electric field has a phase of delta E, magnetic field has a phase of delta B, and the propagation constant has a phase of phi. So, B and E are then related through this equation, because B equal to k E by omega. So, because k and E they are at right angles. So, k into E by omega, if you look at the magnitude, therefore, B is equal to k, then E by omega into e to the power of I phi is the phase for this k, and e to the power of I delta is the phase due to the electric field. So, this is the way that electric field and the magnetic field they are related. So, the amplitude and phase delay between E and B fields, you have this real part of the amplitude of the electric field and the magnetic field, they are related in this way, where the value of k and omega you have to consider. So, this is the connection that this gives you the value of k by omega, and the imaginary part that gives you the phase difference between the magnetic field and the electric field. So, through this figure we tried to depict how the electromagnetic wave is propagating in a conducting medium. You can see that the field amplitude decays as it moves along the x direction, and also the electric field and the magnetic field they have a phase difference as it propagates along the along the conducting medium. So, these are the electric field directions and these are the representation for the magnetic field. So, it shows that the electric field and the magnetic field they decay as it propagates through a conducting medium. That means that an electromagnetic wave cannot propagate, cannot penetrate a conductor, it only penetrates up to a certain depth, which is referred to as the skin depth, and we will try to quantify the skin depth of electromagnetic waves in a conductor. So, in a conducting medium, the skin depth is the distance at which the amplitude reduces to 1 upon E times the original amplitude. So, within the before original amplitude, by saying original amplitude, I mean that before it hits the conducting medium, or within a point before, at a point within the conducting medium, the field, if it is E 0, then after the skin depth the field will be E 0 by E. So, the electric field in a conducting medium, the plane wave solution is E 0 complex amplitude, and this is the decay factor and this is the phase factor, and in the similar fashion the magnetic field has a complex amplitude and a decay factor and a phase factor. So, the skin depth is to account for this quantity, that is by the distance over which this E 0, the amplitude falls to E 0 by E, 1 upon E times E 0, that is I have to put this value to be equal to 1. So, k x into d will be equal to 1, that gives you d equal to 1 by minus k. So, this is the skin depth. This k plus and k minus, they have different significances. K minus gives you the skin depth, whereas k plus accounts for the wavelength of the electromagnetic wave. So, twice pi by lambda equal to k plus, we can write in this form also by putting twice pi equal to 1. Now, for a pore conductor, the skin depth can be written as, to account for the skin depth for a pore conductor, we have sigma, which is much less than omega epsilon. So, k plus becomes approximately equal to omega under root mu into epsilon, k minus will be approximately equal to sigma by 2 under root mu by epsilon. You can see that the skin depth d, which is 1 upon k minus, is equal to 1 upon k minus. If you write, this will become the reciprocal of this quantity, that is 2 by sigma epsilon by me. This does not involve the frequency of the electromagnetic wave, that is, it is independent of the frequency. For a pore conductor, the skin depth does not depend on the frequency of the electromagnetic wave that is trying to travel through the medium. In the case of a good conductor, we have sigma, which is much greater than omega epsilon. This is the way we have defined this good conductor, that is, conductivity is very high. Then this k plus will be approximately equal to k minus, because you can ignore that 1 in the solution of k plus and k minus, then both of them are approximately same. So, you can write this k plus or k minus is equal to this. Therefore, the skin depth d, which is the reciprocal of k plus, will be equal to lambda by twice pi and d equal to 1/6 of the wavelength. So, in a good conductor, the electromagnetic waves only travel through 1/6 of the wavelength distance. The energy density of an electromagnetic wave is given by this, we have seen that. So, if you substitute in the sine cosine solution of the electric field and magnetic field, we can rewrite this equation in this form, and then you can calculate the average energy density associated with the electromagnetic wave is given by this. So, for a good conductor, you can calculate the average energy density associated with the electromagnetic wave is equal to this, and the energy flow is characterized by the Poynting vector, that is S equal to 1 upon mu E cross B. And if we evaluate this expression, where for a cycle the integration is equal to half into cosine phi, in this case it is not equal to half. This is because there is a phase difference between the electric and magnetic field, which is like the power factor. So, it appears in the expression of k plus as k equal to cosine phi. So, we can calculate the Poynting vector in this case as well. So, the average power we can calculate in this form. With the progression of the wave, the energy density decreases with a factor of this, and this lost energy heats up the conductor, which we call the conductor heating. Next, we will consider the average power dissipation in a conductor. Let us consider a slab. In the slab, this power we can write in this form, that E into j delta x into A, j is equal to sigma E square. So, we can rewrite this equation. Now, if you calculate the power, average power, then we can write this equation. Now, let us consider the average power that is flowing into the slab. We have calculated the expression for average power, whether it is going in or going out will be decided by this factor. So, power flowing in will be given by this into A, whereas the power flowing out from the slab, this k minus k into x will be replaced by twice minus k into x plus delta x. So, this factor will account for the thickness of the slab. So, the difference between the power that is going in and going out will give you the power that is lost within the conductor. If you evaluate this equation, you can rewrite this equation in this form using k plus k minus equal to this, which we have seen in the solution for k. So, you can calculate the power loss is equal to this. So, this is how we have discussed the transient decay of the free charge in conducting medium, wave equations and plane wave solutions in a conducting medium, phase and amplitude relations for the electric field and the magnetic fields. We have also classified the good conductor and poor conductor, and we looked at the skin depth for good conductor and poor conductor. For a good conductor, it is only the 1/6 of the wavelength of the electromagnetic wave, whereas for a poor conductor it does not depend on the frequency, and we also have calculated the average power dissipation through a conducting medium, which actually accounts for the Joule's loss in the conductor. Thank you.